Welcome to Petra Soderling Co.'s Quick 5 on Quantum. I'm here with the boss again. Hey Petra, how you doing?
Terrific, thanks.
Good. Okay, let's jump in. What is quantum technology?
What is quantum technology? First of all, it is physics, so it's not computer science. It's based on a field of physics called quantum mechanics, which studies atoms and subatomic particles. In particular, how these subatomic particles interact with each other. There's something called a phenomenon that's called quantum entanglement. That's when two or more of these particles interact with each other, so they form something called the quantum state. And the quantum state of atoms is when magic happens. And this is really cool. So listen up.
Okay.
When you have these atoms and they're entangled, any information that you have in one of these atoms or parts of an atom, the other ones have the exact same information. And it doesn't matter how far apart they are. So you can separate these particles when they are in this entangled state. And let's say one of these particles is on Earth and the other one is on Mars, and they contain the same information. It means you have a real-time information communications channel. So you can use this for communications technologies. You can use it for sensing technologies. You can also use it for computing, because when you have a group of atoms or parts of atoms, excuse me, that are entangled in a quantum state and they all perform simultaneously, you can create a computer that acts very differently from current computers, because current computers compute with ones and zeros, but quantum computers can compute with an infinite number of atoms that are all performing the calculus, the mathematic problem at the same time.
Okay. So why now? So why are we talking about this now?
Well, this year, 2025, is the 100th birthday. United Nations is celebrating 100 years of quantum technology. So the science is old. But what's happened in recent years is that governments have put more money into research. And as there's more research, there's more R&D. So companies also are beginning to be interested in creating products out of this. So we have private money and public money going into R&D, and the field is just accelerating. So we're getting use cases, we're getting actual products that companies can use.
Okay, cool. So, I mean, we talked about what it is. So we haven't delved into. I know there's a word here which is a qubit, but instead I'm gonna jump over a little bit and I want to talk about hybrid quantum classical models. So where can we combine kind of classical computing with like quantum processing?
Yeah, that's a real good question. Because quantum as a field of industry is young, it's nascent, and the technology is just forming. You're going to need classical computers to help build quantum computers, but you're also, in classical computing, we need more and more computing power. So we keep building bigger and bigger classical computers. We're building supercomputers in high performance computing fields. But to enhance even the classical supercomputers, you want to add a quantum computer adjacent to it to expand the computing power. And this is being done now all over the world.
And would it work in the same way? I mean, is it effectively like you could have a quantum processor kind of attached to a quantum computer?
Yes, so there would be separate entities. So you have a quantum processor within the quantum computer, and then you have a classical semiconductor in the classical computer, but they compute together. So they're just attached with a cable, but they can perform tasks jointly. So that expands the computing power.
Okay, so what's holding back the industry? You know, are we talking about what's holding back the scalability of quantum computing at the minute?
Yeah, well, that was really two questions in one, I think. So there's one thing that's holding back the scalability is that, as I explained in the beginning, the way you create the quantum state is that you need to have all these atoms perform perfectly in unison to create the entangled state. The entangled state is very, very fragile. The way you do it in labs is that you manipulate the atoms to start to vibrate, and then they start to create this. And you can do the manipulation in different methods. You can shoot lasers on it. You can put them in very cold temperatures and so forth. But it all needs to happen in a clean room lab environment. So if you have any noise, meaning the temperature is wrong, or there's something, a bit of dirt on your equipment, it's going to break the whole system. So if you have a quantum computer, in theory, that would have 1 million qubits, meaning you have the millions and millions of these particles, and they all have to perform simultaneously, and you just have a tiny bit of noise, you have errors that just go through the whole system, and the whole thing collapses. So it's very fragile. So that's what's holding back building, computers very fast. In terms of industry, but we are making breakthroughs. So we're making technological breakthroughs every week. So that's fantastic. And the pace of the acceleration of the technologies it's accelerating. As for an industry, as for companies, two things: money and talent. So there isn't enough money, because this is still a very high-risk investment for venture capitalists and other risk investors. So they're being careful in investing. Also, AI is hoarding a lot of VC investments at the moment, so there isn't that much money for quantum. And the other thing is talent. Currently, you need a lot of physicists to work on this, and you also need people who may not be physicists, but they need to understand how this quantum technology works. So we need governments to invest in more education. We need companies to train their workforce.
Yeah, I mean, we've seen things like this before in history, haven't we? In terms of like the arms race, the space race. Where countries almost seem to be competing to like who can get there first, who can build the first, who can build the first rocket, who send the first man to the moon. I mean, is that happening with quantum?
Absolutely, yeah. So two things happening there. One is the economic race. Countries want to, build their economies, and they want to have their companies be the biggest and most successful companies in the world. So they're looking into deep technologies for that. But the other thing is also national security. Quantum is a technology that you can use for good, but you can also use it to break encryptions. So there's a race between countries who is building quantum capabilities first that could decrypt the other guy's secrets or protect your own secrets.
I mean, is this then a classic question of, probably of naivety, really, that as a consumer, we kind of want more collaboration between nations on these things so that they happen more quickly? Is that naive to even hope for that?
No, it's not naive. I think it's a very beautiful idea, especially in the world how it is now. We definitely need more love and friendship, but also because when you build these systems, you need to source materials, you need to source components, and you can't make all of them in one country. So you definitely do. You do need your friends.
Yeah, and I guess the creation of all these elements is spread pretty much globally, is it?
It is. Exactly. And then the people also, the movement of people in this field is it's important.
I mean, so we talked a little bit about the economics, about the investment into it. But what about the role of the government then, in terms of economics, but also regulation, ethics?
Yeah, the government has a very important role in terms of regulating how companies can source their materials, their these different instruments and tools. So that's one thing. The other thing is the government, as I mentioned, they need to educate more people in this field. They need to fund. So if there's not enough private investments to fund the research and development, the innovation, government needs to step in to make sure that your country stays ahead. And then finally, government is also a very important customer to these companies at the moment. So government labs are buying these computers, are buying these sensors, are buying these communications technologies because there isn't a private market out there yet.
Yeah. I mean, so how do we get this across to the general public, to me? What's the fun bit? How can we see quantum computing in daily life in the future?
Well, I have a fun fact for you.
Cool.
And I know you're also interested in like when do we get there? So I'm going to answer the same question right now. We're already there. It's a scale. It's not a date in time when, okay, first we didn't have quantum and then whoops, now we have quantum. It's already been there for quite a while. GPS works with atomic clocks, and atomic clocks work in a way that they calculate your point of location, the distance of your location to the satellite that your phone is pinging to. And it calculates the distance and the time. The clock calculates the time, and that's how your phone knows where you are at the moment. So you've been using quantum technology as long as you've been using GPS on your phone.
I mean, are there any other like common ways that people are expecting quantum to kind of enter daily life as well? I mean, are we or at least in the future, are we picturing the idea of like a quantum laptop that we could walk around with?
I think a quantum laptop is very, very far away. It's more like a backdoor hidden technology. Another use case where we use currently quantum already currently is the MIR scan machines.
Okay.
So in radiology technology, so you don't really see it; it's there, but you're already using it.
Yeah. Cool. Well, that brings us to a close on Quick 5 on quantum. I hope it was helpful. It was certainly helpful to me. And thanks, Petra.
Thank you, Chris.
And we'll see you again next time.